history of magnets and the different kinds of magnets and some of the basic properties of magnets and magnetic fields. So this first section essentially. Now we're going to get into what are electromagnets, and this is the real kind of meat here of this first half of this chapter is the electromagnets. So early 1800s, early 19th century, we've got Ørsted, who is doing this research with electricity and his compasses, and let's see if we can get a nice picture of that. Actually, let's just look it up. Ørsted wire. So this is the experiment that he did. You have this wire that's coming up through a table, and it's got a current that's going upward through it, like an electrical current, and he's got all these compasses sitting on the table around the wire, and he noticed that the compasses all kind of turned into this circle around the wire. And that is actually the direction of the magnetic field that this wire creates, it turns out. So what he discovered is that wires create magnetic fields, and that those magnetic fields exist in these closed loop circles around the wires. Where's the North Pole? Where's the South Pole? Is there a North Pole or South Pole? This created a whole new paradigm, a whole new idea about magnets and magnetic fields. Wires somehow can create magnetic fields, even though the wire itself may be made of copper and have no magnetic field itself. Copper is not magnetic. So, very interesting stuff we learned here. Over time, this idea of electromagnetism and its electromagnetic field made by electricity has been used in countless things. It may be the most important discovery for the advancement of mankind ever. I really can say that. It's not that hard to say. Here's one example of how it's used. The MRI machine. Anybody ever had an MRI? Anybody ever been in an MRI room? What's that? Yeah? What do they tell you when you go into an MRI room? What do they tell you not to bring with you? What's that? Yeah, no metal in the room, right? Particularly, they're looking for ferromagnetic materials. They're looking for things that have any iron in them, or similar materials to iron, like zinc or nickel or other things like that. So this big loop right here is actually a huge electromagnet. It's a big coil that they put electricity through. Now, they don't use a coil of wire, they use a coil of superconducting material, which is kind of like wire, but different a little bit. We'll learn more about that later. But they have a current going through here that is extremely big, and it makes a huge magnetic field that goes right down the center of this coil. And that is where the patient is inserted into the machine, and that huge magnetic field does all kinds of things to their body, and particularly the things that the doctors put into the body. It can actually make things kind of show up that normally wouldn't show up. You can actually make the body send out signals that it doesn't normally send out, so that you can look at things and study things and understand things better. So the MRI stands for magnetic resonance imaging. They used to call them NMR, which stood for nuclear magnetic resonance, because it is the nucleus of atoms that is vibrating or resonating when you get in one of these things. But they decided to not use the word nuclear in it because it made people nervous. This machine does not use any kind of radiation as far as like X-rays or gamma rays to look into the body. They actually put a material into your body that will vibrate with the magnetic field. And then those vibrations are the things that they look for. But the magnetic field in here is so strong that if I bring in my keychain, which is on a long lanyard, and I stand at the door of the room, the keys will stand outward at almost almost parallel to the ground as they try to get pulled into the machine. That's how strong this magnetic field is. And most of my keys aren't magnetic. I've got the little keychain is magnetic, the little ring, and I've got a little screwdriver on my keys that's magnetic, but most of the keys aren't. So it doesn't take much to really get attracted to these machines, and it can be very dangerous, in fact. If you ever work around an MRI machine, you should be very careful, because if you get between this machine and a chair, for example, the chair may go flying across the room if it's made of metal and hit you and push you into the machine. It may break you into pieces. Many people have been injured badly by being pulled into these machines by something that got between them, when they got between something and something being sucked in by the magnetic field. And the magnetic field is never turned off. We have 2 MRIs here at the hospital, I believe, 2 MRI machines, maybe 3. We have 2, and the oldest one, the last time they turned it off was maybe 12 years ago, or maybe 7 years ago. They had to do some maintenance on it, so they had to stop the current going through it, and then they started it again, and it hasn't stopped since. They don't even have to keep the current going. Once they start it, it goes on its own. It's kind of amazing. We'll learn about that later, but and their newer one, I think, is 3 or 4 years old, 2 or 3 maybe, I don't know. And they've never turned it off. It just goes and goes and goes. But this is an extension of this idea. Here is a permanent magnet or a ferromagnet of some kind that has a north pole and a south pole, and the magnetic field lines go from the north pole, and this magnet has just been put on a sheet of paper with a bunch of iron filings, a bunch of iron dust, and the iron will line up with the magnetic field. And you can see that the field lines kind of go around from the north pole around to the south pole, and if you could see it in the middle of the magnet, they would be going right down the center in just parallel lines. Now I like to put the magnet under the paper so that it shows those field lines going right down the middle, but they didn't do that. But in this one, what they've got going is they've got loops of wire going around and around and around through this paper, and then they put a current through this loop of wire. Now with the wire that was just going straight, which was here, the current, or the magnetic field went around the wire in loops. But for a wire that goes in loops, it turns out that the magnetic field goes straight down through the middle of the loops. And then as it gets out of those loops, it goes around and outside the entire loop and comes back in. So it looks just like this field, very similar. So scientists started to realize that they could make their own magnets that they could turn off and on as they turned off the current and turned on the current. And that could be quite useful. And they could make the magnet even stronger by wrapping their wire in some kind of paper or plastic, and then wrapping that wire around a piece of iron. Because as the magnetic field was formed in the loop of wire, the iron would become magnetized and increase that strength of that magnetic field. So this is what is called an electromagnetic with a ferromagnetic core, or often called just an iron core. And it makes the magnet stronger. So, this time for a demonstration. How many of you have seen a ring launcher before? A ring launcher. So this is a ferromagnetic, this is an electromagnet rather. Let me get my camera all set up so our student can see this as well. Good words. So I'll plug this in up here. I think I'll use this camera. Okay, now let's go to let's open this up here. Okay, let's use the right camera. And let's find a place where we can. All right, it's upside down. Let's do it right side up. got to mount this camera somewhere where you can see what's going on. Maybe. There we go. Okay, so here's my ring launcher. And the ring launcher is really just you can actually see the coil of wire that's on here. This coil of wire is just, it's got several hundred coils on it. And it's wrapped around a piece of plastic here, so it's not an iron core. And then I've got this ring here that I'm going to put on here. And why this ring jumps is not as important right now as it will be later. We'll learn why the ring jumps later. But suffice it to say that if I turn on this magnet, the ring will jump off of the magnet. And it jumps to a height of maybe 2 feet. Okay? Let's back up a little bit with this camera if we can. Let's see a little bit higher up. Now, if I add an iron core, this is just a rod of iron in here. And I put my ring on there. And then I launch this thing. That thing goes up maybe 6 or 7 feet up because the magnetic field is much, much stronger. Now we'll learn about why the ring jumps later. But that shows that strength of the magnetic field. We could also just use it to attract things, but we'll save that for another day. So, the electromagnet turns out to be a very useful thing. Now, if you've ever seen my favorite electromagnetic tool, and many, many tools have been made with electromagnets, my favorite one is easily the electromagnetic crane. Right? So the electromagnetic crane, I want to watch a video. I love these things. I always loved them when I was a kid. Let's see, where are they going to actually show the crane? I want to see the crane. Don't tell me you're not going to actually show us a real, here's a better one. Come on, go away, video.
Okay, here we are at Miami Art and Mill.
Oh, I love this guy's beard. What a great beard.
The electromagnet.
Didn't you guys love these when you were kids? I always saw these in like movies and stuff. I always wanted to drive one of these so I could pick up a car. And you notice that he can make it magnetic or not. Oh. He's
Suck this shit right up out of the truck.
pulled the bathtub right out of the truck. Old bathtubs were often made of iron. So it's an electromagnet, one of my favorites. But there are many electromagnetic tools, including the disk drives inside of computers. This shows an old floppy disk drive that had the writing mechanism built into the disk. But the disk drive that we use in computers now is separate, or sorry, is all combined inside of the computer, so the disk doesn't get taken out of the computer. And so that's all part of one thing, and there's several of them stacked together. In fact, we should take a look at what that looks like really quick, because it's kind of interesting. Hard drive inside. So if you break open one of these hard drives, what you've got is the first of all the magnetic disks, which are these metal disks here in the middle, and then each one of these arms, which goes on one's on top of the disk, and there's one in between each one of the disks, and then there's one on the bottom. So for this particular stack of 3 discs, there are 5 arms, 2 on the outsides, 3 in the middle, or 2 in the middle, 4 arms. Anyway, looks like there's 5, so there must be 4 discs instead of 3. But anyway, those arms have a little reader head on the end that will both read the data that's on there and write new data on there. But that reader head is electromagnetic. It needs to be able to turn off and on because you want to either magnetize or not magnetize wherever you're at. And so that's a little electromagnet on there. Also, the way that this moves around is by electromagnetism because it uses a motor which also uses electromagnetism. So electromagnetism is everywhere, quite literally, in things that we do. You can see it here. They're using the recording head on tape. They're showing how that leaves these little magnetized regions on tape. So eventually, the scientists started to believe that it was current that was causing all magnetism. Because they figured if current causes magnetism when you've got a wire, then maybe current is causing magnetism inside of atoms. And that is fine to think of as long as you don't believe physics. And honestly, that's kind of what they're going to teach you in just about every class except for physics. I'm pretty sure that's what they teach in chemistry, is that you have these particles that are in that atom are made of, and all those particles are charged, like the electrons and the protons are all charged. And they're all spinning and moving, and that's causing a current, and that's what creates the magnetic field. Well, it turns out that that's a good explanation as long as you don't believe that accelerating particles lose energy. Because if accelerating particles lose energy, and they always do as far as we know, then they couldn't be spinning and they couldn't be going around and around and around. This is the same reason why electrons don't go around and around and around the nucleus. They just are there somewhere, we don't know why. We'll learn more about that later too. There's a lot of stuff we're going to learn about later, so be aware of that. So a lot of people explain magnetic fields by saying, well, charges are spinning and that's what causes magnetic field in charged particles. But they couldn't be spinning according to what we understand. They're just, for some reason, magnetic as if they were spinning. And so we just kind of pretend that there's something in particles that makes them magnetic. We actually call it the spin, even though we know they're not spinning as far as the science we understand goes. And we just assume that it's there and we don't worry much about it. It's just there, so accept it and be happy. Again, this is another one of those mysteries of physics that has not yet really been solved. Why do these particles have magnetic qualities to them? Why do some have more magnetic qualities than others? We don't really know. We have some theories, but we've never been able to really test them and confirm exactly why. So anyway, different kinds of magnetic fields, different shapes from different materials or different phenomenon. However, they all have a very similar kind of feature, and that is that the magnetic field has a tendency to be, has this kind of right angle behavior, we could call it. And we'll see more of this as we move through it. But for example, if you have a current that's going around and around in a loop, the magnetic field goes around and around and around that current loop. And if you put your right hand, your thumb, in the direction of the current, and then curl your fingers around the current, that's the direction of the field, turns out. That's just the way it always is. Or if you wrap your hand around the current, the magnetic field in the center of the current is going upward. That's the way it always works. And in this case, the case with the wire here, if we put our thumb, and they're showing it right here, if we put our thumb in the direction of the current with our right hand, our fingers will go around the wire in the same direction that the magnetic field goes around. So if you're looking down on the wire, it's going around clockwise. If the current's going the other direction, then we have to turn our hand over, and the magnetic field would be going around in the clockwise direction if you look from the top. And we use this rule, we call it the right-hand rule, to kind of help us figure out which way fields are going, which way the loops are looping around things, around currents. And here they give you some kind of the kind of rules for that here. The direction of the magnetic field is tangent to the field line at any point in space. So magnetic field lines are always parallel to each other. They never cross each other. They also say that right here. The magnetic field lines, let's see, never cross. So they say right here. Magnetic field lines never cross. They're always continuous. They're always closed loops. And then the second one here, the strength of the field is proportional to the closeness of the lines. So when we start drawing magnetic field lines, if we are drawing field lines for a stronger field, they need to be closer than they are for a weaker field. Just like electric field lines. So here are some of the right-hand rules we need to think about. Right-hand rule number 1 has to do with how magnetic fields affect electric charges. And this is going to take us to a law called Faraday's law. Is this Faraday's law? No, this is Lorenz's law. The Lorentz force. This is named for a guy, again, named Lorentz. And this law, or this equation, force equals Q times V times B, where Q is the charge, V is the velocity of the charge, B is the magnetic field, so B, we use B for magnetic field. And then the theta is the angle between the magnetic field and the velocity of the particle. So it turns out that the angle between velocity and magnetic field matters. When is this force going to be the strongest? What angle? The sign goes between 0 and 1, so when is the sine of an angle equal to 1? Anybody know? The sine of the angle. When is the sine of the angle equal to 1? The cosine of the angle. Pi over 2, which is 90 degrees, right? So when the velocity and the magnetic field are 90 degrees to each other, the force is the strongest, it turns out. And it also turns out that if the velocity is 0 according to this equation, what is the force between the magnetic field puts on the charge? If the velocity is 0. If V is 0, what happens to this equation? It becomes 0, and then the force is 0. So this law here, or this equation that Lorentz put together for us, tells us a couple of different things. First of all, it tells us that the force is strongest when the magnetic field is going one direction and the velocity of the particle is 90 degrees to it. What does it tell us if the velocity of the particle is going in the same direction as the magnetic field? What if the angle is 0 or 180? What is the sine of 0? 0, right? So if the particle is going parallel to the magnetic field, either in the direction or opposite direction of the magnetic field, there's no force on the particle. So this equation tells us a lot of things. First of all, it tells us that only time that an electric charge feels a force from a magnetic field is when it's moving, first of all. The charge has to be moving. And what direction does it have to be moving relative to the magnetic field? Across it. If it's moving with the magnetic field, it won't feel any force. But if it's moving across it at even the smallest angle, you'll get some kind of force on that charge. And the faster the charge is moving, the bigger the force. The bigger the angle between 0 and 90, the bigger the force. Right? So force is equal to Q times B times B times sine theta. This also can be arranged so that we can solve for the magnetic field if we already know the force on the charge. So you can solve for the magnetic field, B equals force on the charge over the charge times its velocity times the sine of the angle between the velocity and the magnetic field. Turns out that magnetic field has units of force over coulomb meter per second, just like this equation would suggest. And that unit for which is newtons over kilometers per second, we call the Tesla. And 1 Tesla of magnetic field is a lot of magnetic field. And if there was a Tesla of magnetic field somewhere in this room, when you walked by it, your keys would be pulled towards that field if you walked within maybe a foot of it. So it's pretty strong magnetic field. It's not a magnetic field you feel almost ever. If you go down to the hospital and go into the MRI room, you will feel a field of several Tesla. But most magnetic fields that we feel, that we live in, are very, very small compared to this, like millitesla or even microtesla fields. Very small forces. Very small magnetic fields. Another unit that we use is 1/10,000th of a Tesla, which is called the Gauss, and that's used quite a bit as well, because it's so much smaller and makes more sense for us. The right-hand rule is also used when we start talking about how particles move in magnetic fields. Excuse me. First of all, it has to be a charged particle, of course, because that's what we're talking about here. But along with Lorenz's law goes a right-hand rule. You put your thumb in the direction of the velocity of the particle. Then you put your hand, your fingers, in the direction of wherever the field is. And then your palm will point towards wherever the force will be pointing. Now that's the way they do it in this book. There are other ways that you may learn in other classes, but my personal favorite is I put my hand in the direction of the field, turn my fingers in the direction of the magnetic field. Sorry, in the direction of velocity, and then I turn my fingers in the direction of the field, and my thumb points which direction the particle will be going. But it works either way. And we always use the right-hand rule, because if we didn't, then everybody would think differently. We always have to use the same rules for everybody. So here's an example. We have a positively charged particle, and it's moving west. So here's the velocity vector, the green arrow. The magnetic field is north. To use the right-hand rule, we're going to put our thumb in the direction of the velocity of the particle and our hand in the direction of the magnetic field. Now this right-hand rule works for positive charges. So it's going to tell us the direction of the force for a positive charge in this situation. Our palm is now pointing down, so that's the direction this force will feel, this charge will feel from the magnetic field. So as this charge is moving west and it's going through this magnetic field, it's going to change direction. Which direction is it going to change? Which direction is it going to end up going after it goes through this field? Which direction is the force it feels? What's that? Across in which direction? It's already going west. What is the direction the force is pointing? Down. Right? Because that's the right-hand rule. The right-hand rule says you put your thumb in the direction of the velocity of the particle, you put your fingers in the direction of the magnetic field, and your palm will point towards the force that the charge feels. The force feels a downward force. So this particle will no longer be going just west. It will be going west and down, right? And this is why the aurora borealis looks like it does. You have these charges that are moving across the North Pole of the Earth, and instead of just being turned in some direction, they actually get pulled into this weird vortex because of this force that is 90 degrees to the direction they're moving. So they get turned. This one gets turned down, those ones get turned sideways, just because the direction of the field is different there. But regardless, they get turned. This one gets turned downward. And this is what always happens with charged particles in magnetic fields. They get turned. Okay? We'll learn more about that. So in this case, this is a 20 nanocoulomb charge. What would we do if this was a negative charge? What do you think would happen instead of going down? It actually goes up. So the right-hand rule for a negative charge, you just use the right-hand rule and then you use the other direction, up out of your hand for a negative, out the back of your hand for a negative charge. So it would go up instead of down if it was a negative charge. This one does go down. It's a 20 nanocoulomb positive charge. We want to calculate that force. They give us the magnetic field I'm assuming it's the magnetic field of the Earth. Magnetic field of the Earth is something like 10 to the 5, yeah, it's 5 times 10 to the minus 5 Tesla, right here. So there's the magnetic field of the Earth, and it's going 10 meters per second, so there's our velocity. Here's our Q times V times B. And then the sine of theta, the angle between magnetic field and velocity in this case is 90 degrees. Sine of 90 degrees is 1, so that just becomes 1 here at the end, times 1. Multiply all these numbers together and we get 1 times 10 to the minus 11 newtons. Is that very much force? No, not very much force. So this is an airplane that's traveling. It's not going to even feel this force. It's such a tiny little force. But if it's a small particle of maybe a small molecule or a small something else, a small particle of dust, and has a very small mass, it will feel this force. It will actually move it. And that's why those cosmic particles in the aurora borealis do move, is because they can feel it even though it's a very, very small force. Because their mass is so small. So that's the Lorentz force in our first equation. Let's do this problem right here. So this will be our quiz for today. Don't look at the solutions. When we use fields, electric fields and magnetic fields in 3 dimensions, remember that dots represent field that is coming out of the page, and X's represent field going into the page. So get a piece of paper, get a pencil. Let's write down our answers to these questions. We're just going to do the first 3. No, let's do every other one. Let's do A, and let's do C, and then let's do... no, let's do B and D and F. B, D, and F. So what you're trying to do is you're trying to use the right-hand rule to determine which way the force is on this particle that's got this velocity V. Now this one here is going to be a positive charge in B. This one the bottom 2 are going to be negative charges for this quiz. So this one's positive, this one's negative, this one's negative. And you're going to use the right-hand rule to figure out which way the direction of the force, the Lorentz force, on these charged particles traveling through these fields. Okay? Magnetic field going to the right here, going to the right here, going to the left here. Figure out which direction the force will be for your quiz.
You said B and E.
You're going to do B, D, and F. B is positively charged, D and F are negatively charged. Okay? Now remember, this is magnetic field, so if you're not doing what Matt's doing right now, you're probably not going to get it right. What's Matt doing right now? You guys see what Matt's doing? Matt is using his right hand to try to figure out which direction this is going, right? And this is what you'll be doing during the test and during your homework. And people will be wondering what the heck you're doing. We call it physics sign language, PSL. Okay, I'll give you another minute or half minute or so to finish up before I collect them. You're trying to find the direction of the force. That's right. The top one is going to be a positively charged particle moving upward through a magnetic field moving to the right. This one is this one's a negative electric charge moving to the left, a magnetic field moving to the right. This one's a negative charge that is coming out of the page. So the velocity is coming towards you out of the page, and the magnetic field is moving to the left. If you don't remember how the right-hand rule works, I'll move back to that really quick. Right-hand rule works, you put your thumb in the direction of velocity, your fingers in the direction of the magnetic field, palm points towards the direction of a force on a positive charge. Anybody need more time? Okay. Another minute here or so. Welcome to the physics world, where being a dork is the norm. You guys ever seen The Martian with Matt Damon? I just saw that for the first time yesterday. And I love the part where the physicist comes in and explains to them how they can get the guy off of Mars, and he calls the project Operation Elrond. And all the scientists in the room get the joke, but the one publicist, the one lady who's not a scientist and she's just there for making news stories for NASA, she's confused and she says, "I hate all of you right now." The one scientist says, "If this is going to be Project Elrond, I want my code name to be Glorfindel, because it's just a nerdy Lord of the Rings thing." Gotta love nerds. They all think alike. Okay, let's go ahead and finish up what you got here and get it turned in. Put your name on it, the date on it. Today is the 14th, Valentine's Day. Better get to Walmart and buy some flowers before they're all gone. Yeah, it's worse for me because my wife's birthday is tomorrow. So 2 days in a row where I have to. Is it?
I sent her a birthday card and had a little wrap on it. I said, "Piece of meat." I said, "Special sprinkles." I love her.
That is
She might not.
hilarious and kind of frightening when it makes you not want to eat sprinkles. Yeah, I actually spent a few hours 2 weeks ago cleaning out a huge garage that was just filled with mice. Oh, man. You could just smell all around and it was just disgusting. Hate that. Okay. So, let's do this. First one. Which direction do we put our thumb for the top one? Upward. Which way do we put our hand? This way, right? So which way is the force?
Out.
In, right? Out for you because your hand is
Oh, I have to. Oh.
right hand. Left-handed people get really confused.
I have to always use my right.
You always have to use your right hand. So thumb up, fingers out, palm points towards the force on a what kind of charge? Only your palm only points towards the force for a positive charge. The top of your hand used for negative charge. So the next one is going to be the top of our hand, right? So which way do we put our thumb? This way. And which way do we put our hand? This way. We can't do that one. Why not? What does the Lorentz force? What does the Lorentz force say? Sine of the angle theta, right? So what is the angle between these two? The velocity and the magnetic field. It's 180 degrees or 0 degrees, right? And so what does that make the equation equal to? So what's the force on this one? So which way is it pointing? It ain't pointing anywhere, right? Arr. No force on this one. Trick question. How about this one? Which way do we point our finger? Out. Hands. This way. Right? So which way is the force? Downward, right? So this one up here is going to have a motion that's going into the board. The force is in the board, right? This one is going to have a motion that's going out and downward, right? So it's going to go out and downward. This one's going to go up and into the board. Incidentally, what are these ones going to do? What's this one going to do if it's positive? The magnetic field is coming out. So we have down, then out, and if it's positive, it's going that way. What if this one's negative? This way, the magnetic field is into the board, right? And so which way is this one when we push it? It's negative. Oops, it's this way, sorry. This way. So we'll go, if it's negative, and we'll go down, right? And then let's do this one too. Magnetic field, the velocity is in. Magnetic field is up. And if it's positive, it goes this way. If it's negative, it goes this way, right?
On F there, that charge is coming towards us, right?
Yep.
Okay, that's what I messed up.
So this one's coming out. Magnetic field's that way, so it gets pushed down if it's positive, up if it's negative. Did we say down? If it's negative, it goes up, right?
Why didn't you tell us we had to use it?
What's that?
Why didn't you tell us on the right hand when we had to use it right
Yeah, good point. We did mention that in passing. And the reason we all use the right hand is because we all have to think of these things in the same way. You know, whether we live in Czechoslovakia or Madagascar or flat. We all have to think of them. We could have used our left-hand rule and make everybody use their left hand, but then people in let's see, where is that? Not Malaysia. It's can't remember. Some people in certain countries would be excluded from our physics, so we don't use the left hand. All right.
So, just to kind of clarify, the right hand rule, I mean, the field does work in that direction, but it's basically just kind of how we
It's just how we remember it.
remember where it's
Yeah.
going.
Yeah. We had to think of something, and this is what they thought of. This is another example of how physicists have had to be creative with their mathematics. The right-hand rule is a mathematics rule, but it's not what we think of in terms of mathematics. When most people think of mathematics, they think of arithmetic. Arithmetic and mathematics are not the same thing. Okay? Arithmetic is manipulating numbers to calculate other numbers. That's arithmetic. And it's not mathematics. Those two things are not the same. Arithmetic can be involved in mathematics, but mathematics is the use of some method or some methodology to explain something. It's essentially the formation of a language. Okay? So mathematics can use your hand, it can use colors, it can use words, it can use anything. Truthfully. And that's something that has been lost. The study of mathematics in like a math department is mostly just arithmetic. What they should call it the arithmetic department and not the mathematics department. because it's mostly arithmetic. What physicists do is true mathematics. And so, I mean, they still do mathematics in math form. For example, calculus is a form of mathematics, not a form of arithmetic. Because what calculus does is it does arithmetic by using some tricks, by using some rules and some theories. So calculus is more physics than it is math, far more physics. And it was invented by physicists to do physics. It was invented by Isaac Newton. So mathematics can also involve symbols, and it does in physics a lot. We use colors and we use all kinds of things because numbers aren't enough. There's no way you could figure this out with a number. It can't be done. Numbers can't explain directions. You have to use symbols, right? That's the same reason we use vectors. Mathematics explain arithmetic. Vectors can't be explained with arithmetic. A number can't describe a direction, but an arrow can, right? So the same reason we use vectors. So that's a very important thing to us in physics, is representing things not necessarily with numbers. Here's another great demonstration of these ideas. I want to show you a real one. I would love for us to be able to go to see a bubble chamber. I don't know where the nearest one is. Probably in Colorado somewhere. But bubble chambers here they actually tell you what it is. It's a big chamber that's filled with a superheated liquid, usually liquid hydrogen, and they detect particles. They have also a magnetic field across them as well, but they detect particles that are very hard to detect with any other method. Particularly, they detect. They have a tendency to be used to detect antimatter particles. Let's see if I can find a really good demonstration of this. This is probably the best one. This is a huge image, so it's going to take forever to download. But essentially, this liquid, this chamber has screens or windows into it, and these screens where you can see the paths of these particles. Because as these particles come into the liquid, they create a little path of bubbles in there behind them. And the bubbles are not they're not like bubbles of air. They're like little bubbles of gaseous hydrogen or even vacuum bubbles. But the magnetic field that's going through here causes the particles that are charged to go in these different paths, these different curlicue paths, because of the different forces on them. And in some cases, you can actually see where two particles of different charges were created. Right here. Notice that you have a particle, you have a path that begins right here, and then one goes off in this direction, the other goes off in this direction. These are oppositely charged particles right here. And we can actually figure out which way the magnetic field is. In some way. If the velocity is this way, we put our thumb that way, right? And we would put our hand in the direction of the field, and that would show us the force. So the field has to be this way. Let's see, the force is this way and this way, so the field would have to be in or out of the, it's either in or out, right? Because it pushed the particle this way. Right? And you find that's the same for all of these things. And so they put a magnetic field across this chamber, and then charged particles that come through this chamber are turned one way for positive particles, another way for negative particles. And if they have a small path, that means they either had a small velocity or very small mass, or both. And bigger ones have bigger velocities or bigger masses, or both. And then particles that are like this, where they start right here and then they go both different directions, those ones are the ones where we see spontaneous generation of particles from energy. This right here is a matter-antimatter pair. You have one that is positive, maybe this is an electron, it's negative, and this one is a positron. And it starts from nothing. I mean, there was no particle there before, and then it just started. So that's actually a spontaneous Maybe it's not spontaneous, maybe it's induced in some way. But you can see all kinds of cool things happening in these bubble chambers. These particles are very difficult to detect otherwise because they're very high energy particles, very small particles, very tiny particles. But you can get all kinds of really cool things going on here, and people study these chambers just to study these particles. They put these chambers usually near, they usually put them near large accelerators, because near large accelerators is where you can create these matter-antimatter pairs very more regularly. So if you ever have a chance to see a bubble chamber in person, you should go see it. They are kind of cool. Anyway, so here they just have a drawing of one of these. So, if you have a charged particle that is in a magnetic field, and the magnetic field has a wide enough field to it, then all charged particles will end up going in circles, because they will always feel this force that is 90 degrees to their direction that they're moving. And when you feel a force that is 90 degrees to the direction that you're moving all the time, you'll always travel in circles. So you always get this circular turning movement. So let's imagine that this particle that is going around here, which is an electron, starts out here somewhere. Let's say it starts out here. And it's coming towards this field, but this field doesn't exist yet. And right as it enters this field, what does it feel? We have an electron, its velocity is to the right, so we put our thumb to the right. Magnetic field is in to the page, so we put our hand, so let's see. No, which way do we put our thumb in the direction of velocity, and then our fingers in the direction of magnetic field? That's this way, right? This way. So our particle is coming in, put our hand this way for the direction of the field that's in the page. So that means our palm is pointing up, but this is an electron, right? So in this case, I'm going against this picture. Let's come in from the top here, because this particle is going this way, and I need to be going that way. So we're going to come in from the top. There we go. So we're coming in from the top. Our velocity, our field, and our palm is pointing up, but it's an electron, so the force is down. So it feels a downward force as it comes into this field, right? That downward force turns the particle. It turns it down this way. Well, now, which direction is it moving? Now it's moving downward and to the right, kind of, right? And which way is the field? The field is still in. And which way does it feel a force now? It feels a force to the left. Right here, it's feeling a force this way. And then as it turns around this way, the right-hand rule, we put our thumb in the direction of the velocity, our hand in the direction of the field into the page, and it feels a force upward. And then as it comes around this way, it keeps feeling that force inward, 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 inward towards the center of this circle. Right? And the radius of this circle really depends on all three things. It depends on how fast it's moving. If it's moving faster, the circle will be bigger. If it's moving slower, the circle will be smaller. It depends on the mass of the electron. How small the particle is. If it's an electron, it's a very small particle. It would make it smaller, but if we made it a much bigger, like negatively charged particle, this thing would be bigger because the force wouldn't turn it as much. If the charge was bigger, it would turn it more, so it would be a tighter circle. If the charge is smaller, the actual amount of charge, then it would turn it less, and it would be a bigger circle. And then, of course, the strength of the magnetic field changes it as well. If it's a stronger magnetic field, it makes a smaller circle. A bigger magnetic field, it makes a bigger circle. And in the end, you get a circle, and what kind of force holds things in circles? We learned this last semester. What kind of force do we call it? A centripetal force. And centripetal force is equal to the mass that's going in the circle times the velocity squared around the circle, or the speed squared around the circle, divided by the radius of the circle. So right here, we just set Lorenz's law. Sine of theta is going to be equal to 1 because it's the velocity and the field are always perpendicular to each other in this particular situation. Equal to the centripetal force that would keep that thing going around and around and around. And this becomes quite interesting because then we can solve for the radius of any circle made by a charge in a magnetic field. If a charge is in a magnetic field and it's making a circle, This is how you calculate its radius. The mass of the particle times the velocity of the particle times the speed around that surface, tangential velocity, divided by the charge of the particle times the magnetic field strength. And that will give you the size of that circle. This is useful. Let's say, for example, that we keep the velocities the same, the magnetic field the same, and the charge the same on any particle that comes into this field. So everything is the same except for the mass. We can use this to measure the mass. We can use the radius to measure the mass. So the bigger the radius, the bigger the mass. And this is what we call a mass spectrometer. You have a box that's got a magnetic field that's the same all the time, and we put particles into that box, and the particles that come in, we strip one electron off them, so they always have a positive charge of 1, positive 1.6 times 10 to the minus 16 coulombs, because we just rip one electron off them. So they all have the same charge, and then we give them a specific velocity by accelerating them through an electric field. If we give them the same velocity, then every particle that goes into this box that we call a mass spectrometer will go in a different size circle. And if you measure the radius of that circle, you can measure the mass of that particle. If that particle is an atom, you can tell exactly what kind of atom it is. Right? If you have iron, it will make one size circle because iron has a mass of 55.5845 grams per mole. But if you make another one, if you make a circle that's twice as big would have to be cadmium. Because cadmium has twice the molar mass of iron. So you can actually put anything in this box, this mass spectrometer, and you can, like a piece of metal. Put a piece of metal in this box, heat it up, evaporate some of the atoms off of it, and then you can put those atoms through this box, through this mass spectrometer, and they'll go into that magnetic field and they'll make different circles of different radiuses, and from those radiuses you can figure out exactly what that metal is made of. Maybe it's made of iron and nickel and titanium. You would have 3 different circles with 3 different radiuses that correspond to those metals. It's not exactly how it's done because in these boxes we don't put them all at the same speed, we put them all across the same voltage, which creates different speeds for different masses, but it still results in the same thing. We can use a mass spectrometer to figure out what anything is made of. Mass spectrometers are very useful things. Not only that, but we can actually figure out how much of each thing there is. So it's really kind of interesting. Mass spectrometers are desktop instruments that are not very big, in fact, about the size of that printer maybe. You can buy a mass spectrometer that big, put any material you want into it, and it will essentially what it does is it starts up by heating the material and evaporating out atoms from the material, and then putting those atoms through the magnetic field at a certain speed and looking at their radii. Most mass spectrometers are designed specifically for metals because metals you can evaporate atoms very easily. For other materials that are not metallic, you have to be a little more inventive. Because, like for example, a cookie won't necessarily melt. Right? You have to maybe burn it or something like that. But anyway. This is a great example. You have a magnet brought near a TV. Don't try this at home. I guarantee you can try this at home and it won't hurt your TV because I can almost guarantee that none of you have a CRT TV at home. Do any of you have a cathode ray tube television? Do any of you have anything besides a flat screen television that's just thin like this? What? Out in the shed maybe? If you do, there are people who want to buy them. You could sell it on, especially if it's about this size, about a small issue. People who rebuild old video game machines from the arcades, that's what they have to use. They can't use the flat screens because they're not the right. They're not very compatible electronically. So they're always looking for those old TV screens that are small. Anyway, so with these old TV screens, the way they worked is they had an electron gun over here on the left that would squirt out these electrons at high speeds And then they had electrical plates, like capacitors kind of things, that would steer the electrons around the inside of this tube. And then on the front of the tube, they had this glass panel that was coated with phosphorus. Phosphorus glows different colors when it gets hit by electrons. And so the phosphorus would glow and you'd get an image. But you'd have to move the electrons on the screen because you only had one electron gun. And you had to make the whole screen glow. And so this thing would scan up and down the screen all the time, making it glow. And you could actually see the lines back and forth sometimes if it was a bad TV or a bad image. But in any case, if you brought a magnet near one of these TVs, it would redirect the electrons. And it could be really bad for your TV because your TV would try to adjust to fix it, and then it would mess up the screen, so half your screen was on one side and the other half was all garbled up. So you had to be very careful. With computers, they had a button on it where you could reset the screen if that happened. With TVs, they didn't always have that. But anyway, what they've done here is we've got this these electrons that are moving along at 6 times 10 to the 7 meters per second, and they're perpendicular to a magnetic field that has a strength of 0.5 Tesla that you've put next to it here. And you can see that these electrons, instead of following in their original paths, the dotted lines are their original paths, they actually start to follow along these electric field paths in these little coiling circles, right? They go in these little helical circles. We want to know what is the radius of these things. So we need to know the mass. They're electrons, so the mass is known. The velocity, they gave us the velocity, divided by the charge, 1.6 times 10 to the minus 19 coulombs for electrons. And then they give us the magnetic field at half a Tesla. And then we just plug those numbers in and you get 0.683 millimeter little circles, half a millimeter. That would really mess it up, by the way. And that's exactly what happens with the aurora borealis. With the aurora borealis, you have all these particles that are coming in from space, and when they encounter the magnetic field of the Earth, they start going in these little spirally circles around those magnetic field lines. Not such a big deal. That by itself will create some light. But what really happens is when the magnetic field lines are really, really close together, you get all of the particles coming together at the poles. Now, some particles are going to go towards the north, some are going to go towards the south. It really kind of depends on whether they're negatively or positively charged. Some end up going one way, some end up going the other way. But they do end up going towards one pole or the other. Let's see here. Does it matter? Actually, I'm not sure if it matters. I have to do my right-hand rule here thing. Yeah. That's what determines. It's positive or negative. Determines. Actually, I'm not sure right now. I have to think about that because it's three-dimensional. It's hard to think in three-dimensional motion top of my head. But anyway, some of them go towards one pole, some go towards the other pole. And as they all come together, they're all these charges that are accelerating. They're both accelerating because they're going around and around and around in these tight little circles, but they're also accelerating towards the planet. And charged particles that accelerate always give off light, it turns out. They always radiate with some kind of electromagnetic radiation. Again, something that we will learn about later. But that is something that is known, is well known, and that is what is going on there at the aurora borealis. And you can see that it goes right through Alaska. Alaska, you can see it really well. Greenland, you can see it really well. It goes right through Alaska, northern Canada, and Greenland. But another thing that is great about this is this actually protects us from those charges. There are many, many, many of those particles that come from the sun that are not only just particles, but they're dangerous particles. They're high energy particles. And those high energy particles get trapped into these little loops and end up going places that it's not going to kill us, right? Usually they end up going around the Earth entirely Sometimes they end up at the north and south poles, but they're not where we live. Most of the people in the world live right here and can be protected from the exposure to those high energy particles, which are in essence like those high energy radiation particles. Without that, we would all be dead. Without the magnetic field of the Earth, we would all be bombarded by radiation constantly, and cancer would be rampant on the Earth, and all kinds of things would be. I mean, our bodies would just be falling apart from all the damage that those particles could do. Here they show the Fermilab accelerator. I've been to that one. Worth going to see. Here's a tokamak, which is like a small Fermilab accelerator. This one's, maybe the size of this room, and it makes particles go around and around and around. And the way that they keep them going around and around and around is by using magnetic fields in a tokamak. Here they steer particles that are charged around and around and around. Here they're containing particles that are not charged. They may be both charged, but most of the time they're struggling to contain particles that are not charged, like neutrons. Neutrons are not charged, but they are magnetic. So the only way that you can control neutrons is to use magnets, and very strong magnets at that. So these are the magnets out here, and then you have this plasma in the middle that is rotating around and around and around. So it takes us to section 22.6, the Hall effect. We'll leave that for next time, and we'll finish up tomorrow. We're going to finish this tomorrow. No lab tomorrow. We will meet tomorrow. We will not meet on Thursday. Two things that I want to mention really quick. Three things really. I will get the homework up here soon, but I will probably leave a little bit early today. Second thing is science fair is on Thursday. If you're a member of the STEM club, this is a great opportunity for you to volunteer in the community. If you would like to volunteer to help out at the science fair, either as a judge or as a scorer or as a person that helps kids find where they're going or whatever, go talk to Joanna Jacobs. She's in charge of that, or Sally Falcon. So please, members of the STEM club, we'd like to encourage you to do that. The third thing is that we need to meet as a STEM club. So if you would like to be a member of our Science, Technology, Engineering, Math Club, we'll be announcing a meeting soon here. We started work on a mechanical clock on this back table last semester. We never got it finished. We need to try to get that finished. We also need to make our plans for science shows that we're going to do this spring, and for our trip to Lincoln that we'll do this spring. We usually try to go to Lincoln and visit the engineering department during their open house and see all the science and engineering that's being done up there, all the cool technology they work on. And then we try to also visit one other kind of STEM-related place. Last year we were going to go to the museum at the air base up there. We didn't end up going though, so maybe we can do that this year. But we need to make plans for that, and also start requesting funds for that, so we know how many people are going and get people committed to going, and then get the money to do that trial. So.
When would that first STEM club meeting be?
Well, I'll have to figure that out. Probably towards the end of this month, I guess. We'll probably start visiting schools to do science shows in late March, early April, usually into May. We usually start doing those. And the trip to New England, I think, is either in March or April. I can't remember which. I want to say it's March, middle of March sometime. But regardless, we need to get planning and put together some things for that. So keep your eyes open for that. I will make an announcement about the time and everything, a date for that meeting. So just to be aware.
So we get the test this week anytime, or is it?
Yeah, anytime this week is fine. I need to make the test, so I'll do that soon.